Yeah, let's start now. This echo is coming. Hello, hello. Fine. So, so so first of all, the convex optimization problem. The definition I told yes, earlier also. uh, Optimizing a convex function in a convex set. Convex set. Now, mm, so now for a convex function. So what is convex set and what is convex function? Those things are uh, discussed earlier. So for a convex function fx, uh, if x star is a local minimum in convex set omega, then it is also global minimum in omega. And then second one is for a convex optimization problem. FONSO is sufficient. FONC first order necessary conditions are sufficient. So last class I discussed what are the how to optimize the function for the equality constant case. Now we'll deal inequality constant case. So problem now the problem sorry, so the problem of minimizing, sorry, problem with inequality constants. So what is inequality constant? So this problem is like this: minimize f of x subject to one equality constant. So if this fx and this equality constant is there, then this kind of problem we solved last class. We need to find out the so we know how to use the FOMC, then how to use the second order necessary conditions, second order sufficient conditions, and we use that for solving a problem in the last class also. So now one more extra constant is there. This comma g of x, g of x is less than 0, less than equal to 0. So then this is the inequality constant here. So for this case, the conditions, the first order condition, second order condition, all will be changed. Now where this hx hx is a m cross 1 vector function, gx is p cross 1 vector function, and x belongs to real n cross 1. Now sorry. So now we'll define one more thing, that is what is active constant. Active constant is there. So a constant is called active constant is active at x star if gi of x star is equal to 0. So that means this g of x, so we have g of x is less than equal to 0. This is the inequality constant here. Now suppose g is a g is a p cross 1 vector, so it's a p dimensional vector. Okay. Now that means so this g of x can be written as g of x can be written as g1 of x, then gp of x. It's a p-dimensional vector. So okay, and so it should be less than equal to 0 0 dot 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 0. So it will also be a p-dimensional vector. Now we'll take so the constant is active when this so we'll take these different x values. Okay. So for a certain x, that is x star, this gi of x star will be equal to 0, not strictly unequal, but it will be equal to 0. That that point, that x star, so then we'll say that that constant is active on that or at that point, at that x star. Okay. So for certain values of x, some constant may be 0, and we'll say that those constants are active on at those certain values of x. Then so this is the definition of active constant. Now Yeah. So now the definition. Yeah. Sorry. Now one more definition is there. That is, so let extra be a point. Satisfy the constants h of x star is equal to 0, comma g of x star is equal to 0. This is the A condition. Then, and let J be the set of indices small j for which Gj of x star equal to 0, then x star is said to be regular point of the constants capital J. Sorry, constants if the gradient vectors are linearly independent. So that means that earlier for the equality constant case, we said that a point x star is regular if this gradient of hi x star are independent vectors. But for this inequality case also, how to check a point regular or not? So now we'll take one x star value, and we know that for the equality constant we have this gradient of hi x star. Now in addition, we'll check for those constraints in the inequality constant also, that for those constants, like for those j, for those j for which this gj of x is equal to 0. That means inequality constant becomes equality for those values of j, or those for that set of j. We'll find out this gradient of gj x star also. Then we'll find out if this gradient of hi x star and gradient of gj x star are linearly independent or not. So that means I can say again here, suppose earlier we have h of x star, h of x is sorry equal to 0. Okay, so x equal to 0. So for that case, we need to find out gradient of h, and for a certain point x star we need to find out gradient of h of x star. So suppose h is a vector, then we need to find out for all values of this I. So for all values of 1 to m, suppose this is the m cross 1 vector. So then we need to show that these are linearly independent or not. Then we can say that this x star is a regular point. But for for this case for inequality constant also, so out of this g of x, this is less than equal to 0, so this is a p cross 1 vector. So this in this constant we will find out for those values of g, for those values of g, sorry, for those values of g, such that g of jx star is equal to 0 for those values. So suppose this is a p cross 1 vector, so that need not to be p values actually. So that means suppose, so we will find out those values of j for which g of x is equal to 0. Suppose here 10 vectors are there. Out of this only I find out that j equals to 1 and j equals to 2. These conditions are satisfied. That means only two conditions are satisfied. That means suppose this is a g1 of x, g2 of x, g10 of x, this x, these 10 vectors, sorry, 10 functions are there. Now out of these only g1 of x is equal to 0 and g2 of x is equal to 0. Okay, so but all other g3 of x star is less than 0, strictly less than 0. All are strictly less than 0. So then we will take only these two g1 and g2, these two functions, and then we will find out gradient of g1 and gradient of g2, and then we will check these are linearly independent or not. In addition to this condition, gradient of hi, now we will check gradient of this g1, g2 both and gradient of hi, all are linearly independent or not. Okay, this is the extra condition here apart from the equality constant case. Now now we can directly write down now the first order necessary condition. So at starting it may be may feel difficult, but after that, so this writing this first order conditions or after those things it will be easy. So so now the first order necessary condition for inequality case. Okay. So now so this conditions are called also called the KKT. So these are very useful conditions, KKT conditions for the inequality constant case. Okay, so you may see this kind of many times. So now let x star be a local minimum point for the problem minimize f of x subject to hx is equal to 0 and g of x equal to 0. Okay, and suppose x star is a regular point. Suppose x star is a regular point constants for the constants, then there is a vector and a vector mu. There is a vector lambda and a vector mu with such that gradient of f of x star plus jh of x star into lambda star plus jg of x star into mu star equal to 0. So where jh of x star is gradient h1 of x star, gradient h2 of x star, gradient hm of x star. Okay, and jg of x star, the gradient of g1 of x star, g2 of x star, gp of x star. Okay, so now okay, so this is the uh, 1 second. Mm. In addition, one more condition is there, such that at this and mu star. 1 second, sorry, mu star. Why this mu is coming like? Okay, so these are the conditions. So in the first order necessary condition, this is also called KKT conditions, where suppose x3 is a local minimum for the optimization problem. This thing, okay. So we can write down again here. What is the h? H is the m cross 1 vector function. G is p cross 1 vector function. Okay. So for this optimization problem, suppose x star is a local minimum point. Now, first of all, we need to check the regularity. So if x star is regular again, then we can go in this case, this equation, this formula. So we can check that. So if this is regular, then we can write down gradient of fx star plus jh x star lambda star plus jg x star mu star is equal to 0, and in addition mu star gx star equal to 0. So this is the in addition, the addition to uh, so this is the additional constant, additional condition here, which was not there in the earlier. Constant. So so that's all. So now so these are the theory. Now summary, in summary we can write down this thing. So what is the, suppose our this is a minimization problem, minimize fx subject to hx is equal to 0 and gx is less than equal to 0. Now for now at beginning we need to write down the KKT conditions. So what should be the KKT conditions? The KKT conditions should be, so first, what, gradient of fx star plus jh x star into lambda star plus jg x star into mu star is equal to 0. Then second, mu star is greater than equal to 0. Third, third mu transpose mu star transpose g of x star is equal to 0. Fourth, sorry, h x star is equal to 0. And fifth, g of x star is less than equal to 0. These are the constant case. Okay, this is already constant. This thing. So this we am I am writing again. But these whole five conditions are the KKT condition. If you solve this whole five conditions, yeah, if you solve this whole five conditions, then you will get the optimal x star value. Okay. So these are the KKT conditions. Now consider the problem. So suppose consider the problem. Suppose one problem is there. So just now I will use this KKT conditions for that problem. So minimize what 2x1 square. So this is the objective function. So objective function is f of x is equal to, and where this x is equal to only two-dimensional vector, 2 cross 1 vector. Okay, so f of x is equal to 2x1 square plus 2x1 x2 plus x2 square minus 10x1 minus 10x2. Okay, so this is the objective function. We need to minimize this function. Just random function maybe. Yeah, so then subject to x1 square plus x2 square less than equal to 5. Then 3x1 plus x2 less than equal to 6. Okay, these are the conditions. There is no equality constant here, only inequality constant. Okay, now now let us write down this. What is the fx? So this is the objective function. Fx is equal to 2x1 square plus 2x1 x2 plus x2 square minus 10x1 minus 10x2. Now find gradient of partial derivative of f with respect to x1, that is equal to 4x1 plus 2x2 minus 10. Then del f del x2, that will be 2x1 plus 2x2 minus 10, and then partial derivative, I mean double derivative, that is the that is not necessary for this case. Okay, that will be for the second order condition. So this is the first order. Then what is the g is the, so x1 square, so x1 square plus x2 square minus 5, and then 3x1 plus x2 minus 6, all will be less than equal to 0. Sorry, 0. Correct or not? So you can check x1 plus x2, x1 square plus x2 square minus 5 less than equal to 0, and 3x1 plus x2 minus 6 less than equal to 0. So this is the 2 cross 1 vector. Okay, so g size is 2 cross 1. Now what should be the g of x? That will be gradient of g1 of x and gradient of g2 of x. Correct. Now what is the g1? So g1 of x is equal to this thing. This is the g1 and this is the g2. So x1 square plus x2 square minus 5. Then gradient of g1 of x. So by this thing we can write down gradient of fx is equal to del f del x1 del f del x2. That is equal to 4x1 plus 2x2 minus 10, 2x1 plus 2x2 minus 10. Yes. So then okay, And similarly here also del G1, del Gx1, del G, sorry, del X2. This thing that is equal to 2x1, 2x2, and del G2x that is equal to gradient of G2x that is equal to del G, del G2, del X1, del G2, del X2. It is equal to 3 and 1. Correct? 3x1 plus x2, right? Yeah. So, so jg of x is equal to gradient of g1, then gradient of g2. So gradient of g1, then gradient of g2. That is equal to gradient of g1 is 2x1, 2x2. So 2x1, 2x2, then 3, 1, 3, 1. So this is the matrix, 4 cross 4 matrix. Sorry, 2 cross 2 matrix. So we got all those values. Now we'll put 5 equations. We'll just use these 5 equations. Okay, these 5 equations. So first one, gradient of f of x star. Gradient of f of x star is first. Gradient of f of x star. That is this thing. Okay. So 4x1 plus 2x2 minus 10. 2x1 plus 2x2 minus 10. So 4x1 star plus 2x2 star minus 10. 2x1 star plus 2x2 star minus 10 is the gradient of fx plus del jg. Here there is no h, okay, only g. So jg is 2 cross 2 matrix. So 2x1 3, 2x2 all are stars, 1. Then here mu1 star, mu2 star is equal to 0. 0 means 0 vector. It's a two-dimensional vector. That means 0 and 0. Okay, so this is the first condition. That means we got two equations. 1a. What is 1a? 4x1 star plus 2x2 star minus 10 plus 2 mu1 star x1 star plus 3 mu2 star is equal to 0. Then 1b, 2x1 star plus 2x2 star minus 10 plus 2x2 star, sorry, 2 mu2 star x2 star plus mu2 star is equal to 0. So these are the two equations. Okay, we got two equations. Now put the second condition. Second condition was just mu star greater than equal to 0. Okay, that means mu1 star is a vector greater than 0 equal to 0. So mu2 star also greater than equal to 0. In third condition, mu star transpose gx star is equal to 0. That means mu1 star, mu2 star, g1x star, g2x star equal to 0. Sorry. So that means mu1 star, mu2 star. What is the g1 x star? G1 was x1 square plus x2 square minus 5, 3x1 plus x2 minus 6 is equal to 0. That means mu1 star into x1 square plus x2 square minus 5 plus mu2 star into 3x1 plus x2 minus 6 is equal to 0. So this is the third condition. Okay. Then fourth condition. So there is no there is no equality constant here. So here there will be only four conditions. So four condition is just inequality constant. That means g of x star is less than equal to 0. That means x1 square plus x2 square all are star minus 5 less than equal to 0 and 3x1 star plus x2 star is the 4a. So these are the whole conditions. These are the whole KKT conditions. So these are the whole KKT. So we can write down here KKT condition. Okay. So these are the whole KKT conditions. So if you solve these conditions, then you can find out the optimal x1 star and x2 star. Okay. So let us solve this thing now and check which will be the candidate point of I mean what will be the x1 star and x2 star. Okay, so it will be a lengthy solution. Okay, but this is the solution. I mean this is the some general solution. Uh, so you can apply this whole same formula, same conditions for any kind of optimization problem. So now condition sorry consider four cases. Now how to solve this thing. Okay, so it will be difficult to solve. Now consider four cases. One one is mu1 is equal to 0 and mu2 is equal to 0. Let's start. Okay. Number two, mu1 is non-zero and mu2 is equal to 0. Number three, mu1 mu1 is equal to 0, mu2 non-zero. Both are non-zero. So one is both are zeros, one is non-zero, another one is non-zero, then both are non-zero. So there are four cases we will take. Okay, first case, case one, case I, mu1 star is equal to 0 and mu2 star 0. For this case, let us solve the problem. So suppose mu1 star and mu2 star both are 0. Then how will you solve? Then from the one equation, from one. So from one, so from one, uh, mu1 and mu2 both are 0. Then 4x1 star plus 2x2 star minus 10 equal to 0 and 2x1 star plus 2x2 star minus 10 equal to 0. So that means 4x1 star plus 2x2 star 10 equal to 0 and 2x1 star plus 2x2 star 10 equal to 0. This is the one A and B. Okay. So this is the from one. Okay. Now Now solve this thing. Okay, there are two equations and two unknowns. So we can solve this thing. Solving, solving, solve. So ultimately you will get x1 star is equal to 0 and x2 star is equal to 5. Okay. Now this is the from 1. Now from 4. From 4, what is 4? 4 is written like this. So all four conditions should be satisfied. 1, 2, 3, and 4. Suppose this is the four conditions. So these all will be this x1 square plus x2 square minus 5 is less than equal to 0. Okay, so 4a x1 square plus x2 square minus 5 less than equal to 0 should be satisfied. Satisfied. Now you put this thing. Uh, this x1 is equal to 0, so 0 plus x2 square is 25 minus 5 less than equal to 0. That means 20 less than equal to 0. So it's not satisfying. So it's not satisfying this condition. So then this point, this should not be a candidate point because these are not satisfying all four conditions. Only one condition it is satisfying, but fourth condition is not satisfied. So then so x1 star is equal to 0 and x2 star is equal to 5 is not feasible solution. So then this first case is gone. Now let's take case 2. Okay, case 2. For the case 2, mu1 star is non-zero. Mu2 star is equal to 0. This case, okay. So now from 1, you will get 4x1 plus 2x2 minus 10 plus 2 mu1 x1 is equal to 0 and 2x1 plus 2x2 minus 10 plus 2 mu1 x2 will be 0. This is the 1a, 1b, and then from 3, so 3 is written like this only. 3 is this thing, this equation. Okay. So now mu2 is 0. Then you will get mu1 star into this equal to 0. So mu1 star to x1 equal to 0. Okay, this is a equation 3. So okay, so now so mu1 is non-zero, correct? So that means this is 0. x1 star plus x2 square, 2 square minus 5 equal to 0. As mu1 is non-zero. So now we got three equations. This is equation 3a. Let's take. So this is the 3a, 1a, and 1b. So you can solve three equations and three unknowns: x1 star, x2 star, and mu1 star. Then how will you get? So ultimately the solution is solving solve 1a, 1b, and 3a. So three equations. If you solve the solution, you are getting x1 equal to 1, x2 equal to 2, and mu1 2, 1. And then this is the 1. Second one is x1 equal to minus 1.72, x2 is equal to minus 1.42, mu sorry mu1 equal to minus 5.63. Minus 5.63. But the thing is that here in the condition 2, should be positive only. So then this is not feasible. As mu is negative, so not feasible. But this thing is fine. So this is the feasible solution. So this is the candidate point. Candidate point for local minimum. Okay. So um, okay. So this is the case 2. Now case 3 and case 4, if you solve case 3 and case 4, if you solve in this way, then you will get no feasible solution. Okay, so only one candidate point. So this is the candidate point for local minimum. Okay. Now, if the second order sufficient condition is satisfied on this point, then we can say that, oh, okay, this is the optimal point or local minimum point. Okay. So that's all for the KKT conditions. Now, sorry. Now SONC and SOSC show not directly. So I will write down the second order sufficient condition directly. Let x star belongs to r power n, comma lambda star r power m, mu star r power p be the vector satisfying KKT conditions. KKT conditions. Uh, Suppose the components of mu star. Suppose the components of mu star positive corresponding to the each of the active inequality. Positive constant for every vector y in the subset m of x star, if we have y transpose L of x star lambda star y greater than 0, then is a strict local minimum of the function fx. So subject to constant. Okay, so this is the second order sufficient condition. So for a function fx and constant hx is equal to 0 and gx less than equal to 0, let x star and lambda star and mu star be the vector satisfy kkd condition. So after the first order necessary condition, so let us take that 1 minute. Yeah. So how to find inverse of the pilot matrix? Okay, so I'll show how to find out that pseudo inverse. Okay. Uh, so for a function, okay, so so after satisfying the KKT conditions, we'll again find out, we'll again check the second condition is this condition, and if it is satisfied, then we can say that x star is the strict local minimum. Okay. And for y belongs to this subset m of x star. How to find m of x star? We know that we in the last class we did that thing. So okay, and sorry. So yeah, one more thing is that yeah, so this thing actually, so one mu is zero. So in the case two, one mu star is non-zero, another mu star is zero. So that means ultimately we are getting this equation only. From three we are getting this, and another mu star is zero. So that means in case of out of two inequality constant, one is becoming equality constant, another is becoming inequality itself. Okay. So that's what he's saying, that I mean that's what it's mentioned in the second or sufficient condition is that mu star is positive corresponding to the each of the active inequality constant. That means suppose mu one star is non-zero, but mu one star should be greater than zero also, should be positive also, greater than equal to zero. So here, so that's why we are taking greater than equal to zero. Negative is not feasible. So that's mentioned here again. And then extra is the strict local minimum if this condition is satisfied. Okay. Now quickly we'll check that this problem is second or sufficient condition is satisfied or not. Let's quickly check that thing. uh, okay. So the candidate point is was so candidate point was so problem continue. So candidate point. Okay. Sorry. Oh, X2 is 2 or 1? 2, 2. X2 is 2, not 1. Now we need to find out this thing. Sorry. L of x. Okay. What's the L of x? Now Asian of x. Asian of x is equal to 4, 2, 2, 2, and is equal to the Asian of gx. Okay, it means 0, 2. So L of x is equal to 4, 2, 2, 2 plus mu 1 into this thing 2, 0, 0, 2. So if you do that thing, that is coming 6, 2, 2, 4, 2, 4. Okay, and find out that so y1, y2, then 6, 2, 2, 4, y1, y2 is equal to what is this? 6 y1 square. Sorry, sorry. Mm, So 10 y1 square, 6 y1 square. Yeah, correct. 6 y1 square plus 4 y1 y2 plus 4 y2 square, and again equality constant should be satisfied. So that means this thing. That means this, and then y 2x1 y1 plus 2x2 y2 equal to 0. That means x1 is 1 and x2 is 2. So 2y1 plus 2 into 2 into y2 is equal to 0. So 2y1 plus 4y2 0. So y1 plus 2y2 is equal to 0. So or we can write down y1 equal to minus 2y2. Okay, now let's put here. So that is equal to 6 into minus 2y2 square plus 4 into minus 2y2 into y2 plus 4y2 square, that is equals to so minus 6 sorry, not minus 4 24 y2 square minus 8 y2 square plus 4 y2 square, so that is equal to 20 y2 square. So this is already greater than 0. So that means mm, uh, so SOSC is satisfied. SC is satisfied. So x1 star, sorry, x is equal to 1 and 2. So is a strict local minimum point. Okay, so now okay, let's jump to another topic, that is the so in the last class I didn't cover one topic, that is regularized least square. So suppose so least square problem, you know that what is the solution. I did that in the last class. So least square problem is that minimize norm of x norm of x and norm of x square subject to y equal to x. So this was the problem. Solution, you know that solution, you know. Also professor has done it, and professor has done this thing again also, regular list also he has done it. So again I'm saying that, so for the regularized least square, for the regularized least square, what the problem is that minimizing the distance, correct, y minus x square subject to not subject to, minimizing this plus one more constant. So this constant again power. Okay, So this is the energy and this is the error. So yeah, so this is the problem, and solution is the he has mentioned that thing. So suppose this is the fx. Okay, so A transpose A plus lambda I into x minus 2x transpose A transpose Y. Now gradient of, so yeah, one more thing. Yeah, one more thing. Why we are studying the convex optimization problem? Because here, if you notice that this norm is norm square is a convex function. We have discussed earlier. Norm is a convex function. So this objective function is a convex function itself. So this is a convex function itself. Convex function itself. So then we are finding the first order necessary condition. You may have questioned that why don't we go for the second order sufficient condition? We should go for the second order sufficient condition, right? After that we can say that this point is the local minimum point or not. But in every cases in the first class onwards we are doing we are finding only the first order condition, right? We are applying first order condition. So the thing is that for the convex function, I told here also for the convex function, FONC itself is sufficient. That means if the KKT conditions are satisfied or the gradient conditions, those conditions, I mean first order condition is satisfied, then we can say that, oh, okay, so this condition, this is the optimal point. Okay, there, so we need not go to the go to check the second or sufficient condition. Here I mentioned here also. See, for a convex optimization problem, FOMC conditions are sufficient. So those are the itself sufficient. Okay, we need not go to and check the second order sufficient condition. Okay, that is the point here. That is the point why we are only finding out the first order necessary. We are only applying the first order conditions and finding out that point and saying that that is the optimal point. Okay, because of this convexity of the function. Okay, now we'll find out the gradient of f of x. Sorry, gradient of f of x is equal to 2a transpose a plus lambda I minus 2a 2a transpose y. Okay, now the problem was that we can, so a gradient of f of x star plus jh of x star into, so there is no jh, this is 0. So this is unconstant optimization. So this would be only equal to 0. So that means A transpose A plus lambda I minus A transpose Y is equal to 0. Now we can write down A transpose A plus lambda I equal to A transpose Y. One minute. This will be X here, right? X here. There will be X here. Yeah. So then X star can be written as X star can be written as is equal to A transpose A plus lambda I inverse A transpose Y. This is the solution. Okay. So this is a solution. Now we'll go to another topic. There is a linear program. Linear programs. Okay. The problem. So let's condition the problem. Let's take the problem. Problem minimize C transpose X subject to A's equal to B and X greater than equal to 0. Okay, so this is the problem of least square problem. This is a least square problem, and sorry. So this X is n cross 1 vector and B is m cross 1 vector and A is a matrix of dimension m cross n. So that means the problem is kind of this actually. Minimize f of x. Objective function is C transpose x subject to hx that is equal to ax minus b that is equal to 0 and gx equal to minus of x is equal to 0. So this is the problem, optimization problem. Now KKT conditions we need to write down. How to solve this optimization problem? Correct? KKT conditions. First condition. And you see that this is the convex function. Okay. And this is also a convex set. So then this is the convex function. You can check that from the basic convex function, convex set. Again, so that means the convex optimization problem. So that means KKT conditions or first order conditions are itself sufficient. No need to go for second order conditions. That is the advantage of convex function or convex optimization problem. So the convex optimization problem. KKT conditions are like this only. So if you find out the KKT conditions, the basic KKT conditions, you can write down gradient, then all those things. Okay, J, H, J, G, finding out those things, then lambda, mu, all those things. If you do that thing, you will get ultimately A transpose lambda star plus mu star is equal to, sorry, C. Second one, mu star is greater than equal to 0. Third one, mu star transpose X star is equal to 0. Fourth one, A X star is equal to 0. Sorry, X star equal to B. Fifth one, X star greater than equal to 0. So these are the five conditions. Okay, if you solve five conditions, then you can get the optimal point. Okay. Now, second problem, just the second problem, the problem minimize P transpose X subject to so all are inequality. There is no equality here in Gx. So for that case also KKT conditions. Okay. So actually this linear program we can find out the dual dual problem also, and then we can solve that problem and solution will be same. So in the next class I will deal with the dual problem, how to find out the dual problem. Those are the so I mean the important topics, how to find out the dual problem and optimizing the dual problem also. So KKT conditions, first condition is A transpose lambda star plus mu star C. Second is mu star 0, lambda star is equal to 0. Third condition, mu star transpose x star to 0, lambda star to ax star equal to 0. Fourth condition, x star is greater than equal to 0. Fifth condition, x star is bigger than equal to 0. These are the KKT conditions. Okay, I'm just did away. I am just what avoiding uh, the derivation. So these are the KKT conditions. Now, MIMO beamforming. So multiple antenna. So transmitting antennas are multiple, and there are so many transmitting antennas and there's so many receiving antennas also. So suppose this is the transmission side, this is the receiver side. So this is the transmission receiver side. So suppose transmission side antennas are T cross one, and then here R cross one antenna. So the receive vector is equal to h into this s vector plus n. Okay, so where s is the transmitting vector, and here y. Okay, so then we can write down. Okay, now the thing is that now transmit beamforming. For the transmit beamforming, we will send one vector v for the same x. Okay, and okay, so that means receiver we are getting h of h v x plus n. Okay, and receiver beamforming we can do. That means y tilde will get, that is equal to some u transpose into y. Okay, so that means u transpose h v x plus u transpose n. Okay, so this is the problem. So now let h is equal to h into v. That means y tilde is equal to u transpose hx. Sorry, it is not vector, plus u transpose n. Now, sorry, now what should the optimal u? So this is the just kind of receiver normal receiver beamforming for earlier what we have done, right? So this thing actually, so the solution will be h norm of h. So then output SNR to maximize relative to all be subject to. So solving this thing will get the ultimately. I'm just avoiding the derivation. Professor has already done it. So ultimately, we are getting that V is equal to eigenvector corresponding to a maximum eigenvalue of H Hermitian H transpose H. Okay, is the thing. Now sample problem. So in the sample problem, I will solve then two problems only. Okay, one is how to find the pseudo inverse, what you have told that problem, and then one more is that for the least square also one more problem, and for the linear program, the problem I will solve in the next class, because yeah, in the next class I will solve that problem for the linear problem, one or two problems, and that will come maybe in the assignment 9 maybe. So after that you will get time for the assignment. Okay, so that means linear program I can do next class, I will do next class. And okay, so the sample problems, so what you have said, that how to find out the pseudo inverse of what is the question? Hmm, how to find inverse of pilot matrix. So okay, so let's wait for 1 minute. I need to find out the question. Okay, so what should be the? I mean, let's take a pilot matrix. Let's 1 minute. The question is 1, 2, 3, 4. 1, 2, 3, 4. 4 cross 2. Is down is what is the solution? Solution is answer is 1, 4, 1 by 4, 1 by 4, 1 by 4. Mm-hmm. Same, same. Okay, fine. So so inverse of pilot matrix. So suppose there is a matrix. Okay, suppose P is a matrix. 1 minute. I am. Is the tips? You messaged me on chat. How to find inverse of pilot matrix? Pseudo inverse. Yeah, yeah, correct. Pseudo inverse only. Yeah, yeah. So let's take a pilot matrix. Okay, P that is equal to some 2 cross 3 matrix, 3 cross 2 matrix. Okay, let us take 3 cross 2 means, suppose uh 1 1 1 minus 1 1 minus 1. Let us take this matrix 3 cross 2, and find the pseudo inverse of, what is the pseudo inverse of P. Okay, so see here, this P is a full rank. That means these two columns are linearly independent. Okay, so these are the linearly independent columns. That means rank is full. That means rank of P is equal to 2 only, full rank. full rank. Sorry, full rank. That means P transpose P. This is invertible or non-singular. Invertible means that means its inverse exists. Okay, invertible. Okay, because P transpose P, if you see, this will be 2 cross 2 matrix, and 2 cross 2, as rank of P is 2, then this P transpose P will be invertible. So okay, now what should be the P transpose P? 1 1, sorry, 1 1 1 minus 1 1 minus 1 into this thing, 1 1 1 1 1 minus 1. 1 1 1 3 minus 1 1 minus 1 minus 1 1 0 minus 1 minus 1 1 1 0 minus 1 minus 1 minus 1 1 1 1 1 1 1 1 3. Okay, now P transpose P, and okay, and pseudo inverse is for this case pseudo inverse, we know that that's P dagger, that will be equal to uh, P transpose P inverse P transpose. Okay, so we need to find out inverse of this. So what should be the P transpose P inverse? Inverse of 3 minus 1 minus 1, 3 inverse. That means determinant is equal to 3 9 minus 1 8. So 1 by 8. Transpose of which these 3 minus 1 3, then plus minus 1 plus. So that means 1 by 8, 3 1 1 3. Okay, okay. Now C2 inverse beta is equal to P transpose P inverse. P transpose that is equal to 1 by 8 3 1 1 3 1 1 1 minus 1 1 minus 1 equal to 1 by 8 3 minus 1. This is 2. 3 minus 1 2. 3 plus 1 4. 3 plus 1 4. 3 minus 1 2. 1 minus 3 is minus 2. 1 minus 3 is minus 2. 1 plus 3 is 4, and then 1 minus 3 is minus 2. That is equal to 1 by 4, 1 2 1 minus 1 2 minus 1. So this is a pseudo inverse. So P pseudo inverse is equal to 1 by 4, 1 2 1 minus 1 2 minus 1. Okay, let me check, is it correct or not. Actually, there is one website you can find online how to find out the pseudo inverse also. Three cross. In MATLAB also you can find out. So yeah, correct only. So so this is the process you can find out the pseudo inverse. In the assignment, maybe you need to find out some pseudo inverse, some defined matrix actually. So the process is same. You can find out. Then in the second question is that. So you get it right. The second question is the consider the least square problem. With e is equal to with error is equal to y minus x. So the question is e perpendicular to range space of a. So this is the range space. Okay, so the solution is yeah, it's perpendicular because after that we are getting only the normal equation. So the thing is that suppose uh, this y equal to y minus x. Okay, suppose this oh, oh, this is the column space of a. So this is the x. Okay, and suppose so this is the y. Okay, y equal to x plus this. So this thing and this thing. Suppose this is the ag and this is the error y minus a. Okay, so this error is perpendicular to this x. So E is perpendicular to y minus x, y minus x perpendicular to x. That means y minus x transpose x equal to 0. So that means uh, ay. Uh, So AY is the AX. Yeah, correct. So the thing is that so so AY. So that means AZ transpose this Y minus X equal to 0. It means uh, Y transpose for all Z. Okay, so Y transpose that means Z transpose A transpose Y is equal to Z transpose. 1 second. That means Z transpose A transpose Y minus X. So that means Z transpose A transpose Y minus X is equal to 0 for all Z. Okay, so that means this A transpose AZ. So as this all Z it is true, then A transpose uh, Y minus AX equal to 0. That means A transpose AX equal to A transpose Y. Yeah, done. So these are the normal equations. So ultimately, using this error, this normality condition, we can also deduce the formula again. Okay, so these are normal equations. Yeah, that's all for today. So if you have any doubt, you can ask me. And how to find out the pilot matrix inverse, pseudo inverse of the pilot matrix? I think you have understood. You can ask me if you have any question. So at the beginning I told that what is the convex optimization problem, and for the convex optimization problem, what is the advantage of the convex optimization problem. Okay. For the convex optimization problem, the local minimum itself will become global minimum, and we need not check the second order sufficient condition. First order necessary condition itself is sufficient. Okay. And then so this is the first order necessary condition. For the inequality constants, we have 5 conditions. These 5 conditions are necessary. All the words, all those things you can omit. Just 5 equations, 5 conditions, KKT conditions. Those are the useful in everywhere. Okay. And so suppose this problem I have taken. So how to find out the a normal problem? It need not to be a convex problem. It's just a problem. So I founded. I have used. I have so I derived the 5 KKT conditions here, and then I used the second order sufficient conditions. Okay, and told that, and found out that matrix is positive definite, and so and or hence the point is a strict local minimum point. Okay. And sorry. So then least square problem, regularized least square case. This is the solution of regularized least square case. And then linear program. So how to find out the linear program, solution of linear program? These are KKT conditions. And one more thing, dual problem. I'll do that thing in the next class. And this is the MIMO beamforming. This is the one application of optimization, convex optimization problem actually. So this is the MIMO beamforming. And sample problem, how to find out the pseudo inverse of the pilot matrix. And then second one is that this error is perpendicular to the range space of the matrix for the least square problem case. Okay. So that's all for today. If you have any question, you can ask me. Or did you understand how to find out the pseudo inverse of the pilot matrix?
Yes, sir. Thank you, sir.
Okay, okay. Thank you. So yeah, that's all for today. So we can leave the meeting now. So thank you and have happy weekend.
Sir, how to find the channel estimator H matrix, sir?
H matrix. How to find the H matrix? Okay.
X is given, Y is given, then how to find? channel estimator.
Okay, okay. Oh, so this question. Okay, okay. See,
Please explain with the example.
suppose this you're saying that sorry. So hx plus n. So y is the data. This is given measurements, and x is also given. So how to find h? Correct or not? This one, not vector case. Let us take first a scalar case. It will be easy. Okay, so y is equal to hx plus n. So uh, y given, x given. So that is called a pilot. And then how to find h? H will be what? Right, this question, right?
Yes, sir.
Okay. So so the find how to find age. So here we can optimize. We can find out the mean square error, minimum mean square error estimate. Okay. Uh, suppose how many h is there. So we can minimize the distance between y and h. Sorry. What? Okay. So first let us take mm, the distribution. So
So take one example and explain, sir.
okay, okay. Okay, first let me derive the question. Then I will take the example and I will solve that problem. Okay. Okay. So solution is kind of this actually. Suppose then expectation of uh, okay, mean square means. Oh, here this is the okay. This question. So here you can use this itself actually, this list square itself actually. Okay. So I need we need to find out what is the age. Okay. So that this error is minimum. Okay. So this is a least square problem. So minimum with respect to age. Okay. So age will be what? Age will be so for the case of y minus y. So y minus ax. Okay. That case. Okay. So x was a transpose a inverse a transpose y. Okay. Here this a is becoming x actually. So h will be x transpose x inverse x transpose y, and here all are scalar, so x square. So inverse means 1 by, so xy by x square, that means y by x only. So yeah, so that is the solution for this case. So yeah, understood. So you can use this least square problem itself. So y equal to hx plus some noise, and what will be the h hat? H hat will be y by x. Okay, so suppose this problem is that so y equal to so this is the solution just. Okay, so you need to, so y you know, and then just divide by that by x actually. For but for the vector case, just use this equation. Okay, so this a transpose a inverse a transpose x. Okay, did you understand? So just divide that by x actually. So I can take one example, but just division by x, y by x.
Y is one of the vector, X is also one of the vector. How to
Okay.
find?
For that case, okay. So this is a scalar case. Now let us take for the vector case. So Y is one of the vector and X is also one. What? Can you repeat the question? Yeah. Hello.
Yes, sir. Y is one of the vector. X is also one of the vector. Then how to find channel
Y
estimate?
is a vector. Acha. This. Then you are saying this matrix. How to find this matrix?
Y
Huh?
is 2 cross 1 or 2 cross 4.
I understood. So y is a vector. Suppose 2 cross
Yes,
1 and x is also a vector. Suppose some 2 cross
yes.
1 also. Then h is a 2 cross 2 matrix. So you're saying that how to estimate this matrix
Uh,
using this system model.
data. Okay. Yes, sir.
But so that MIMO channel estimation. So that channel estimation, you can't do this using this way actually using this system model. So actually here you can find what should be the x with known h with known matrix. So the solution is the least square solution. But if you need to find what should the h matrix using this system model, you can't do that. That can be done using some other technique like compressed sensing, some other technique, some sparse channel estimation. So those kind of techniques can be useful. Here you can't find out that matrix. Okay. Is there any question on in the assignments like this?
Yes, sir.
Okay, which question? Okay, I don't have. Okay, so so can you 1 second? Let me open the question in first. Uh, Let me open the assignment question first. Yeah, I just want to see that is that question is.
Consider a multi-antenna channel estimation scenario with a pilot matrix X and received vector Y given as X is 4 cross 2 matrix is given, Y is 4 cross 1 matrix, sir. Hello, am I audible?
Yeah, sorry. Yeah, so 1 second. Let me search the question. So you're saying that
X
consider
is
him.
pilot matrix, Y is received vector. X is given as 4 cross 2 matrix, Y is 4 cross 1 matrix.
Oh, consider
We have to
multi.
find the channel estimate.
Understood. Yeah, yeah. This question. Oh, multi antenna channels estimation scenario with pilot matrix X and receive vector Y given as. Okay, okay. So pilot matrix X. Oh, this question. Actually, here this is nothing. This is not related to this system model. Actually, this is not related to this system model. This is just related to the least square problem itself. Okay, so the
Okay.
question is like this actually. So that's what I'm thinking. So the question is like this. So here the pilot matrix is X. Okay, this is the matrix. Okay, so that means the question is like this only. X y equals to X into H plus some n. Okay, so it's similar to y equals to A into X plus some noise. Okay, so that's similar to finding the X using this Y, where A is this matrix. Okay, that means it's nothing but just pseudo inverse of X multiplied with Y. You understood? This is the solution.
Okay.
Okay, so
Okay.
actually this is the question from the assignment, so I can't do it directly, but this is just a least square problem. Okay,
Sir, you can take another value.
another value. Yeah, this is the solution. So I found
Okay.
out the least square, right? This is the least
Even
square.
matrix is X or X plus. Okay, sir.
Understood, right? So this is the pseudo inverse. You just need to multiply this kind of matrix into this vector. Or what is this
So we
vector?
have to find the pseudo inverse.
Y.
Okay, sir. Thank you.
Okay. Yeah, yeah. Thank you.
Okay,
Yeah,
thank
yeah.
you.
Okay. Thank you. Yeah.